All right, so we're in 7.5 today, and this section does not introduce any new techniques for integration, but instead what we're looking at is a strategy for integrating a function when you're given an integral to solve. So the idea here is to take the techniques we've already learned and kind of decide how we should approach an integral using those techniques. So to begin with, I have this table here. It includes 20 common integrals that we already know. These are basically, not all of them, but most of these are integrals that you should have memorized by this point, just because they show up pretty frequently. The two that I'm going to say you don't necessarily need to have memorized are the last two, so 19 and 20. And the reason for that, you'll notice there's these little asterisks here. This is straight out of your textbook, and the author kind of puts a little side note for those last two. Both of these can be solved by using, one of the techniques we've talked about. So for example, number 19, you see there's a difference of squares down here. That means you could factor that denominator, which implies that you could use partial fractions to solve any integral that looks like this. But, this is a general formula that will work for all possible integrals that take this form, for any value of a that you want to put there. So if you know this is kind of a shortcut, but you don't necessarily have to memorize it. This one can also be solved using the appropriate substitution. A hyperbolic substitution can work in cases like this, or the appropriate trig sub. It just kind of depends on what the integral looks like, but this is sort of a general form for integrals of this type. Okay, so let's get into the strategies, kind of a 4-step thing. And we're just going to go through this step by step and then work through a few examples to sort of see how it works. So step 1, when you're given an integral to solve, what you want to do first is simplify your integrand if it can be simplified. So in this example right here, we're taking the integral of the square root of x times 1 plus the square root of x. Now, by itself, you might be able to solve this with some kind of clever u substitution or something like that, but that's kind of overkill, because really, if you just distribute that square root into both terms, you end up with root x plus x. And you can use the power rule, or the antiderivative version of the power rule, to solve this in a very straightforward way. Another common place where simplification of your integrand really helps is when you're dealing with trig functions. So here, we're taking the integral of tangent of theta over secant squared. And using some basic trig identities, we could simplify this down into a simpler form. So for example, tangent of theta over secant squared is the same thing as this. If we rewrite tangent as sine over cosine, and remember that secant squared is the reciprocal of cosine squared, and because it's in the denominator, we could write that as cosine squared times that sine over cosine. Do a little cancellation here, so we're left with sine times cosine. And then you could do this with a u substitution, or you could recognize that this looks very similar to the double angle formula for the sine function. Sine of 2 theta is equal to 2 times sine of theta cosine of theta, which would mean that this is actually 1/2 sine of 2 theta. This is super quick to solve, but simplifying the integrand was necessary to get us to that point. And here's another example where simplifying your integrand is really helpful. I'll let you read through that one on your own. But the point there is sometimes you need to do a little bit of algebraic simplification on your integrand before you really should attempt any kind of techniques, any kind of integration techniques. Okay, so next up, coming down to step 2 here, look for an obvious substitution, okay? So what it's primarily referring to here is like a u substitution. So really, u substitution is the first main integration technique that we talk about beyond just finding an antiderivative by inspection. And it's an incredibly useful technique. We continue to use it oftentimes in conjunction with these other techniques that we've talked about in chapter 7. So as a first step, you tend to want to look for that u substitution before really attempting anything else. So if you look at this example right here, I'm trying to integrate x over x squared minus 1. Now, we just finished a section in 7.4 on partial fractions. And if you notice, the denominator here is a difference of squares. So it could factor to x plus 1 times x minus 1. And it might be tempting to do that and then start creating a partial fraction decomposition and integrating that. That absolutely works. You can do that. But that is a lot more work than you need to be doing, because an alternative approach, which takes a lot less time, is to notice that the degree of my denominator is 1 greater than the degree of this x here, which suggests that we should try using u equals x squared minus 1. If you do that, then your du is equal to 2x dx, which is so close to what you have here. You can just multiply both sides by 1/2, and you have a very usable u substitution. So that would solve that integral way faster than partial fractions would. Okay? Step 3. So if you've simplified your integrand and you've looked for a u substitution, and maybe you haven't found a u substitution that just makes short work of the integral, this is where we want to start looking at which of the techniques in chapter 7 might be the one to try. And this is not a foolproof step here, because sometimes integrals require a technique that's not obvious. But in a lot of cases, we can decide what technique to use by classifying your integrand according to its form. So as an example, in section 7.2, we looked at a lot of integrals of trigonometric functions, mostly trigonometric functions raised to some power. So if you're seeing that in your integrand, if you're seeing trig functions raised to some power, like powers of sine or cosine or tangent or secant, or cotangent or cosecant, then we can think about how we handled those back in 7.2. We still use u substitution a lot, but there's some guidelines as far as how to choose u in those cases. So that would be, a form that we know what to do with. Rational functions. If you've already looked at a rational function and decided, I don't see an obvious u substitution here, kind of like on the previous page for step 2, then that might be the time to try doing partial fractions and splitting that rational function up into simpler rational functions that you can integrate more directly. Integration by parts. So integration by parts, remember, typically involves a product of functions, which you may not be able to take care of with just a direct u substitution. So common examples are if you have a power of x times like an exponential function or maybe a logarithm or something like that. We saw that integration by parts works for integrands of that type. Then radicals, specifically radicals that have a particular look to them. So radicals like, square root of x squared plus a squared, or if you have an x squared minus a squared, or the reverse of that, a squared minus x squared. We've seen that trig substitutions are really useful in those cases. So if you recognize the form of your integrand as one of these types, that suggests trying a trig sub. And then this, I think we've seen a little bit of this, but if you have a radical of the form ax plus b, so a linear polynomial under an nth root, then you can make that entire thing your u as a u substitution, and sometimes that helps solve that integral. That's not a guarantee, but depending on what the rest of your integrand looks like, you might be able to do some algebraic manipulation with this to create a substitution that works. Now, step 4, try again. So integration is not like differentiation. In Calculus 1, you spend most of your time dealing with derivatives. And derivatives, even though they can take a long time to do depending on the function you're differentiating, are generally, they generally don't require any creativity, any trial and error. If you know what you're doing, it's a straightforward thing. You have rules that tell you exactly how to differentiate all sorts of different functions. Integration does not work that way. Sometimes it does. Sometimes integration is very straightforward, but lots of times it takes a good amount of creativity and trial and error to end up solving an integral that you're trying to solve. So for that reason, your first approach may not work. And the important thing is to not give up at that point. Not to say, well, I tried this technique, it didn't work, so that must mean I can't solve this integral. In all likelihood, there's a different approach that'll help. Okay, so here's some basic guidelines. If you've already tried something, what should you try instead? So substitution. Now that was step 2, right? Try an obvious substitution. If you've looked at your integrand and you've decided, I don't see an obvious u substitution, there might be a less than obvious substitution that works. In fact, our first example, I believe our first example in this section will be one of those. It may require you to be a little bit more creative with what you're setting u equal to make this work out. Okay? Another example is trying integration by parts. So we have seen a couple of examples now where integration by parts can actually help with an integrand that does not look like a product of two functions. Usually integration by parts is used when your integrand looks like a product. But if you recall, back in 7.1, we found the integral of the natural log of x, which is just the natural log of x by itself. We set u equal to the natural log of x and dv just equal to dx. So even though it didn't seem like a candidate for integration by parts, when we tried that, it worked. It gave us an integral. It gave us a solution, rather. Okay. Part C is kind of like step 1. So step 1, remember we said simplify your integrand. And sometimes simplifying the integrand, it's a little bit vague what we mean by the word simplify. Sometimes there's a little bit of subjectivity there. So occasionally you may have an integrand that doesn't look too complicated as it is, but it's resistant to your integration techniques. So when we say manipulate the integrand, what we mean is do some kind of algebraic operation on it, which may make it more complicated looking, but the more complicated version of this integrand might be easier to integrate. So this is an example. If I want to integrate 1 over 1 minus cosine of x. I don't see an obvious u substitution that would help, because if I set u equal to cosine of x, or 1 minus cosine of x, for example, then I would need to be seeing a sine of x dx in here for my du, and I don't see that. So instead, what we're going to do is manipulate this integrand a little bit before we try doing any actual integration with it. And this is going to use a trick called multiplying by a conjugate. This is something you do in Calculus 1 as well. It's very helpful when you're learning about limits. Sometimes you're evaluating the limit of a rational function, which is hard to evaluate as written, but then if you multiply by something called a conjugate, it puts it in a simpler form. So when I say conjugate, what I mean here is looking at this denominator, 1 minus cosine of x. If I multiply my numerator and denominator of this rational expression by the same expression here, but swapping the minus out for a plus, or if this was a plus, swapping it out for a minus, I would call that expression the conjugate of this one. So you notice I'm multiplying by 1 plus cosine of x, 1 plus cosine of x. It's okay to do this because this rational expression is equal to 1, and multiplying by 1 doesn't change anything. Well, the benefit of doing that is that my denominator, when I multiply things out, becomes 1 minus cosine squared. That I recognize as part of my Pythagorean identity, which I can convert to sine squared. Okay, my new numerator becomes 1 plus cosine of squared, cosine of x, not cosine of squared, sorry. So my integrand now looks more complicated than it did here, but I can manipulate this a little bit more to put it in a form that's ready to be integrated. So if I split this up, I can rewrite it as cosecant of x squared, or cosecant squared, plus cosine of x over sine of x. Both of these can be integrated very easily, because the antiderivative of cosecant squared is negative cotangent. That's ready to go. This one, I can just use a u substitution, set u equal to sine of x, so that du is cosine of x dx. I already have my du like ready to go. So manipulating your integrand is something we tend to do a lot when we've already tried a couple of things. Okay. Another example, we're going to see one like this in the examples that we do, is relating the problem to previous problems. We have done several examples of evaluating integrals up until this point. And you're going to see that some of the integrals that we have worked out keep reappearing in different contexts throughout the course. So here is an example. If you want to integrate tangent squared times secant of x dx, you can use a Pythagorean identity to write tangent squared as secant squared minus 1, and then distribute that secant in, giving you secant cubed minus secant of x. And now you can break that up into two integrals, which you're subtracting. You can integrate secant of x dx just by looking at the table that we had on the first page. There's an integral for that. Secant cubed is a little tricky to do, but we have actually done that. We have evaluated secant cubed of x, its integral, already in, I believe, 7.2. So if you go back to our lecture notes for 7.2, you'll see what this is equal to. That secant cubed of x, I think I've mentioned, shows up somewhat frequently in integration problems, not like all the time, but you're going to see it pop up here and there. You don't want to go through all of the steps of evaluating it every single time you encounter it. Instead, let's just remember or have written in our notes somewhere what this integral is equal to. And so that if it appears in a problem like this, we don't have to do the integration by parts and all the other stuff that we did before. We could just go straight to the solution. Okay, we're going to see an example in this section where we have to do that as well. And then finally, use several methods. So sometimes, like I said before, the first method that seems to be the right one doesn't seem to get you anywhere. Or maybe you use a method and it seems to kind of be sending you in the right direction, but maybe there's more that needs to be done. Sometimes an integral requires multiple techniques just to solve. So you might have a problem where you first need to make a u substitution, and then once you make that u substitution, it's a little bit more clear that the new form of your integrand is easier to integrate using a trig substitution or something like that. So you may find yourself using a combination of techniques depending on the example you're doing, okay? So that's kind of the gist of our strategy. In the next video, we're going to take a look at 4 examples of integrals and try to incorporate this strategy.